So now we know what vector fields are, and we also know how to quantify an electric field. So why don't we look at what an electric field looks like on a graph. So there are two ways of representing electric fields. Each provides us with different information. So we're going to take a look at both and then go through some practice as to how we can draw the electric field lines if we're given certain point charges in different areas in space. So with electric fields, there are two main ways to visualize them, each giving different information. So let's go with different, there are two different ways of visualizing E fields. So one, we have a set of arrows. Let's call this a set of vector arrows. So if we take a look at this, it's very useful for the magnitude and direction of an electric field at specific points in space. So every single vector is associated with a position in space. So if we want to know how strong the field is and what direction it's pointing in at a specific location, for example, right over here, then this would be a good representation to use. Another one is if we did have, let's say, a similar electric field like the one here in blue, instead of having individual arrows, we could have electric field lines. So these are electric field lines, or basically tangent lines to vectors. So if you take a look closely, these are basically the tangents to all the vectors, and it's an approximation of all of the tangents of those vectors when we draw a line through all of them. So these would be good for observing flow, and also the more lines that occupy a certain area of space, so the more dense the lines are, the stronger the electric fields. So the density of line, is proportional to the strength of the electric field. So those are the two different ways of visualizing these electric fields. Now we want to look at how to figure out the direction of these electric field vectors. So in order to know what direction they point in, we have to look at our point charge Q again, which can be positive or negative. So this is, how do we know which direction the vector points in? We look at our point charge capital Q, which can be positive or negative, and bring in a positive test charge. So let's go through the two different options we have. We have an option where Q is a negative value, so Q is less than 0. We also have another option where Q is positive and therefore greater than 0. So if I put a point charge here and here, let's say. Let's go with the negative test charge Q first. Its interaction with a positive test charge, negative and positive attract, which means that there's going to be an attractive force that's felt by the point charge. So wherever I put this point charge in, if I put the point charge all over here, so I take a bunch of tests, it's going to experience an attractive force. And the farther away we get, the smaller this force becomes. So that would be summarized by saying the total charge, or not the total charge, the test charge plus Q will experience an attractive force. Now let's take a look at the other option where our point charge Q, capital Q, is positive. So our test charge also has to remain positive so that we can make comparisons. And what kind of force will the test charge here feel from a positive charge? So a positive charge and a positive charge are going to repel each other, so it's going to experience a force this way. The closer the test charge is to the point charge, the larger the magnitude of force that it's going to feel. And all that it's going to feel is a repelling force. Like this. So test charge Q will experience a repulsive force. So in other words, just by looking at these two drawings, it seems like for a negative charge Q, it acts like a vacuum, like it's sucking in all of the, it's sucking in the electric field lines. And then for a positive charge Q, it's radiating outwards. So your electric field radiates out of positive charges and gets sucked in by negative charges. A few other things to note. The electric field is proportional to the charge. So the larger your charge, the larger the magnitude of the electric field being radiated outwards or inwards. Your electric field is also proportional to 1 over r squared. So that means the farther away your point P is, where you're applying that test charge, the smaller the electric field will be at that point. A few other observations we can make are that charges, so capital Q, are the sources of electric fields, like we've shown here with the two drawings. Electric fields radiate out of positive charges and into negative charges. The electric field lines are going to look like fine hair blowing in an electric field wind, which we'll show in a bit. And we can locate charges if we can see an electric field distribution. So, for example, if I took out the positive Q over here, and you had all of those electric field vectors radiating out of some sort of empty spot over here, then we can deduce that there has to be some sort of positive charge that's creating all these electric field vectors radiating outwards. So let's go through a couple of examples just to solidify our understanding of electric field vectors and field representations. So number one, let's draw the electric field lines for these charges. Let's say I have a positive charge and then I have a negative charge, like this. And let's say they're of equal magnitudes. So some things we know are that electric fields must radiate out of positive charges and they must radiate inwards towards negative charges. So let's draw a few field lines coming out of our positive charge. And let's draw the same number of field lines, and these should radiate in towards our negative charge. So the interaction between the two, this is going to radiate outwards and go straight into the negative charge, like a vacuum. This means this would also do the same, as well as this. This one up here would go out and in, like that. You'd have these ones going like this. And this is just an approximation. And if I added a few more field lines, this one would go here, and we could have more like this, just as an example. So then here, you'd also have oops, probably better to have this. You want all of the arrows pointing this way towards the negative charge, except for this one line coming from some source towards the very far right, where it radiates into the negative charge here. So now, this was a really simple example where you just have one positive charge and one negative charge. And as you can see, you have all of the electric field lines radiating out of the positive charge and into the negative charge. Now we want to draw an electric field line for multiple charges. So we want to have something a little bit more difficult, just so we can see how these charges and the electric field lines are going to interact with each other. So let's say I have a -3 charge here, and a +3 charge over here, and maybe a +1 over here and another positive 1 here. So for fun, you can always just draw a whole bunch of different charges on a blank sheet of paper and just play around with electric fields to see how they would interact. So now I take a look at my, let's say, positive 1 sources first. And let's say there's just something like this. So I'm just drawing 8 electric field lines radiating outwards because it's +1. A +3 point charge would definitely have more electric field lines radiating outwards. Triple the amount of +1. I don't want to draw that many, so let's just draw twice as much. And that means we'll have something similar with our -3. Okay, so something along those lines. So starting here, we now know that there must be an attractive force between +3 and -3. So why don't we start with that? Let's draw a straight line from +3 to -3. Say these two seem to be straight and can be connected to each other. Then you have these ones and these ones. That. Okay, so we have a few that we have right now. Seems like these ones would go like this. Okay, so why don't we stop there? Let's try and take a look at the other interactions from the positive charges. So why don't I take a look at +1 and -3? There has to be a direct line connecting the two of them, and that means that this would go into here, and this would most likely go into here as well. So this would go into here. Oops. And this one would go into here. And then you'd have other charges, or not other charges, the effects of the other charges radiating inwards towards your -3. And let's say this one is one of those that would go around and go here. So it's just because we can't draw every single field line coming in and out. So it seems like we've gotten most of the interactions with -3 covered. The only things missing are these two, so we want to finish this off and connect it to this. Okay, so we've completed all of the lines that go into -3. Now we have to move on to the +1 at the bottom that we've completely neglected for now. And that +1 charge at the bottom is going to be repelled from both of the positive charges to its left and right. So that means this line over here, this electric field line, has to find a way to escape from all this. And if it travels this way, it's going to be repelled by the +1 at the bottom and repelled by the +1 at the top and go in this direction. This can be really similar for this one. We can go here, here, and like that. And the rest would just be repulsive forces, like this. Oops, let's draw this a little bit better. So you'd have all of these repulsed lines like this. That means there's a problem when this comes out. It's going to hit this electric field line and want to go here. And you have something similar for all of these. This is going to come here and repel like that. So now we have our +1 at the bottom finished. We now need to complete the +1 on the very left. So this electric field line is going to come out here and get repelled, and so will this one. So now all of our electric field lines are finished, and we get a complete picture, and we can start to put different test charges. For example, if we put a test charge here, plus Q, we'll be able to say what kind of electric field or electrostatic force it experiences at different points in space along this entire electric field. So give that a try. There are apps that you can use, such as through Lab 1, where you can view the electrostatic or electric field vectors. Draw a couple of charges out of different magnitudes, and of course different polarities, positive or negative. Try drawing the electric field lines and double check your work using those applets, and that gives you really good practice.